Some things to think about as we go into the final. First of all, we spend a lot of time solving equations in this class. What does it mean to solve an equation? So the solution to an equation are the values of the variable that make the equation true. In solving an equation, we're using algebraic techniques to isolate the variable. Which algebraic techniques we use depends on what type of equation we're looking at. And what we're doing are a lot of inverse operations. We're undoing things. So write down as many things as you could think of that might help you to solve an equation. And here's some matching. It's important to be able to recognize what type of equation you're looking at in order to know what sort of techniques you want to use. So we've got a list of different types of equations here, and then a list of a whole lot of different equations. So which ones are which? This one here is pretty easy because we've got those telltale vertical signs that tells us this is an absolute value equation. This one also, because it's got all these rational expressions, is a rational equation. And the one with the square root, that has to be a radical equation. This one, the variable's up in the exponent, so it's an exponential equation. This one, this is a nice one. There's no powers, there's no roots, nothing messy, no fractions. This is a linear equation. This one's a little harder. This is what we call a literal equation. So it's a formula. When we solve for f1, we'll have to use the techniques of clearing fractions that we'd use with other functions, but our answer is not going to be a numerical answer. Our answer is going to be another formula. So literal equations, we don't have values for all the variables in the equation. We're solving for one of many variables in the equation, and what we're essentially doing is taking one formula and rewriting it as a format of another formula. Okay. This equation has an exponent, and the exponent happens to be a fraction, or rational function, a rational value. So that's j involving fractional exponents. This one I think everyone should recognize as a quadratic, though notice that it's not in standard format. And if it's got logs, it's got to be a logarithmic equation, and this one's a polynomial equation. So think about trying some of these that you need to work on and solving those. Okay, and doing a little brainstorming here, think about the first steps that you need to do for each of these different types of equations. Linear equations, we simplify each side, we try to isolate the variable. Quadratics we want to have in standard format. And then if we can factor, that's usually easier. We can always fall back on the quadratic formula. And some of you are going to prefer completing the square over the quadratic formula. Literal equations, we're isolating the variables using some of these other techniques. Radical equations, we isolate the radicals, square both sides and solve, and watch out for extraneous solutions. So something that's quadratic in form is something that would say be like x to the 6th plus 3x to the 3rd. Something that would actually be factorable, and then but when we factor it, we won't have x equals 3, we'll have something like x squared equals 3, x cubed equals 3. So we need to finish it by taking the appropriate root of the variable. The fractional exponents, try to isolate the variable expression with the fractional exponent and raise to the reciprocal exponent. So the expression's to the power of 2/3. If we raise both sides of the equations to the power of 3/2, that will undo it. Rationals, fractions, and I should have put a note in here, we also need to watch out for extraneous solutions on rational equations. Absolute values, isolate the absolute value. Whatever constant it's equal to, set it equal to both that constant and the negative of that constant. Polynomials, factor if you can, otherwise it's a little more detailed on the next page. Exponential equations, isolate the expression with the exponent, take the log of both sides, that's what undoes the exponents. And logarithmic functions, get that out of the way there. Isolate the log, then write in exponential form. Okay, solving polynomial equations. This is something that some of you got down cold and others of you are still struggling with. So finding the zeros of a polynomial. So 3 connections to make. If you have an x-intercept, if a0 is an x-intercept, then x equal a is a 0, and x subtract a is a factor of the polynomial. So finding zeros, we usually start off with using our calculator to graph the function, look for any nice x-intercepts. And the possible rational zero theorem comes in handy here sometimes, trying to interpret if that x-intercept is a fraction, what fraction it might be. Then we use synthetic division to both determine if a value is actually a zero of the polynomial and also to kind of start factoring down the polynomial. We repeat that step 2 using the synthetic division as many times as we can, and we often need to use the quadratic formula to finish out the problem or to find the last two zeros of the polynomial, especially if the zeros are irrational or if they're imaginary. And then inequalities. It's been a long time since we talked about inequalities. The linear inequalities are not too difficult to solve. Essentially isolate the variable, but watch out. If it's necessary to divide both sides by a negative number in solving it, we have to reverse the sign here, the inequality. Only if we divide by a negative. If we're dividing by a positive 5, we would not need to do that. Absolute value inequalities, solve them two different ways depending on whether we've got a constant greater than the absolute value or if the absolute value is greater than the constant. If the absolute value is smaller than the constant, then it should be in between the positive and the negative of that constant. And we solve it like a three-sided equation to isolate the variable in between two constants. If the absolute value is greater than a constant, then our solutions are going to be out on what we call the tails of the number line. So we set it equal, not equal, set it greater than the constant or less than the opposite of the constant, and solve for the variable on both sides. And then quadratic inequalities. If we can factor, we factor, otherwise we use a quadratic formula to locate the critical values. You can't trust the signs to come out correctly on quadratic inequalities, so we have to then check using the critical values as our boundary values, and then we pick test values in each of the three regions and see whether or not the test value we picked actually works in the original problem. And then whatever intervals of values actually work, that's our solution. So our solution here is from -2 to 6. Rational equations are very similar. Find the critical values, so either what makes the numerator to 0 or the denominator 0 will be our critical values. Use those to define our test regions. Pick a value in each test region, check, see whether or not they satisfy the original inequality to get our solution. Here we don't want to include -3 in our solution because -3 would give us a 0 in the denominator, whereas we do include the 5/2 because 0 in the numerator is fine because we've got a less than or equal to 0.